Well, welcome to the Friday afternoon colloquium. It's my very great honor to introduce our speaker today, actually someone who you guys probably know very well, Dr. Mihai Gherase. So Dr. Gherase got his BS and MS in physics and medical physics at Bucharest University, and then he got his PhD in 2006 at Carleton University in Canada. And he's been with us since 2014. Very successful in research and grant getting, and is refreshed after a nice sabbatical. And today he's going to talk to us about medical and biological investigations using synchrotron radiation. So let's welcome Dr. Gherase.
Thank you, Doug. Thank you for the invitation. So yeah, synchrotron came about, I think, in my second year of postdoc, and David Fleming, where I was working, we said, oh, maybe we should look into that because that's something that we can do in the future. And so I have to basically thank David for introducing me. We actually went, both of us went to a summer school in 2008 at the Canadian Light Source, which I'll talk about. It's the only synchrotron I've been to, but they're made in the world. So I'll give a bit of layout. I'll talk a bit about the synchrotron and the synchrotron radiation. History, synchrotrons around the world. There are about 50 right now in the world, and I'll focus only on two methods that I've been more familiar with, and I work with X-ray fluorescence, which is my main field of research, and X-ray absorption spectroscopy, which is related to, and you'll see a nice applications in biology. And then I'll give a few samples of medical and biological XRF and XIS applications. So yeah, as I mentioned, in 2008, I was at the summer school at CLS. I also got sucked in writing a review paper a few years ago, which I regret because it took a lot of time and I realized how much work is done in synchrotron. But anyway, a lot of, most of the presentation is based on that. There is a huge amount of work done with synchrotrons. So what is a synchrotron? Well, it's a type of particle accelerator. It's a descendant of the cyclotron, which was discovered or worked on in the 1920s and 30s by Ernest Lawrence. It's actually still used a lot today for making radioisotopes, artificial isotopes. You can accelerate particles and protons mostly, and then bombard certain nuclei and produce artificial radioisotopes that are used. A lot of them are used in nuclear medicine, particularly that they can produce positron emission nuclei that can be used in positron emission tomography. And so you see that some big research centers like hospitals have this cyclotron. Now cyclotron, how it worked basically, we had these, you apply an alternative electric field. So when once you can basically, when a particle comes from left to right, it's accelerated. When it comes from the other side, accelerated again because of the cyclic part of the electric field. And the magnetic field that's applied this way basically keeps the electron in motion. The problem with the cyclotron is that you cannot reach very high energies because at some point, when you compute what frequency you need, you realize that the mass increases as you get to high energy. It depends on the velocity. So at some point, you no longer have this synchronicity between the alternative electric field, and you would have to make this very, very large. It breaks down. So that's where synchrotron came about, and basically what it does is synchronizes the electric field and the magnetic field. So the magnetic field keeps the electrons and other particles, protons, in basically localized, it bends them, and the electric field accelerates them. So it's basically a particle accelerator. The radiation, what is the synchrotron radiation? Well, once you accelerate the electrons, if you bend them in a magnetic field, you can produce electromagnetic radiation. There is a long history that spans almost a century, starting with Maxwell equations. Well, that basically proves that moving charges can produce electromagnetic radiation. In fact, he derived from his equation that the electromagnetic radiation is connected to the electric and magnetic fields. Hertz demonstrated that not long after J.J. Thomson discovered the electron at the end of the 19th century, and two guys, Alfred Liner and Emil Bickert at University of Groningen in Paris, they came up with the retarded potential idea. So what happens when a charge moves, accelerating or moves in general, what happens to its electric and magnetic fields? The person who basically came up with the mathematics of how how electromagnetic radiation comes from an accelerated charge was this guy, George Schott, who was a mathematician at Cambridge. He actually won for this essay, Electromagnetic Radiation, he won the Adams Prize at Cambridge University. And he's basically credited with actually theoretically discovering the electromagnetic radiation produced by accelerated charges. In the 1940s, scientists in the former Soviet Union, they basically came to look at accelerated charges, and they basically said that if you have a betatron, which is a different type of accelerator, you have a limit on it, because if accelerated charge starts to lose radiation, then you have a limit on how much energy you can give to that particle. In the same time, almost in the same time, two guys, they actually came up with the synchrotron idea. So they discovered the synchrotron in 1945, and very shortly after, a group at General Electric, led by Herb Pollock and his collaborators, they had the first experimental observation of the synchrotron radiation. And they use a small 70 MeV synchrotron. And the team is here. There are some other, pretty big names. Langmuir, who actually won the Nobel Prize for Chemistry, surface chemistry, and they have a journal named after him, is here. And a few others. You see the size of this synchrotron, it's only like not even a meter in diameter, so very, very small. And they actually said in the figure that it's the worst second synchrotron. So the first one was developed in England, and then the second one was developed by General Electric, and they were the first to discover radiation, observe experimentally the radiation. In terms of theory, so this is the Russian paper that was published after the initial work, then the observation of the General Electric group, and then Julian Stringer actually put all the work in. He developed the theory for electrons in any type of geometry, how if you accelerate electrons in any type of geometry, what is the radiation, what is its characteristics, and it's been used ever since to actually look at how you can design synchrotrons, how the electron beam has to be, what is the magnetic field, how it's the best to produce a certain electromagnetic radiation. Now, moving to today's world, so this was 1940s first synchrotrons. It was kind of a slow start with just a few countries having synchrotrons. Now there are about 50 in the world. There is even an organization, it's Light Sources, and you can actually see the orange basically show which synchrotrons are part of this organization that has about 30 synchrotron facilities. You can look, on the website they give a lot of, what the output of science, like 170,000 papers. They can determine the structure of 115,000 protein, and they have 7,000 voice types, so, and pretty big. And you can actually see, we're here in California, you see the Stanford synchrotron, you see also the Canadian up here and some others in the US. In terms of how the distribution is, if you look actually, US, Japan, and Germany have about half or more than half of the synchrotrons in the world. There are some older facilities that got dismantled just because they're too old. And you see some other countries that have about one, so there are a few who only have one. Newer, like even Poland, Eastern Europe, and some other countries like Brazil, so developing countries. India has two, Italy, and so on. Europe has also concentrated quite a few synchrotron facilities. Here in the US, we have basically two main places, national labs. You see, for example, the Argonne, it's a large one. outside Chicago, and we have the Lawrence Berkeley, that actually is part of it's very famous Berkeley. And then you have universities such as Cornell, Chess, the Cornell Synchrotron, and then of course the Stanford, which is one of the first in the US.
Mihai,
Yes.
are they only used for research or?
They're used for research and in industrial applications. You pay money, you can pay for up to $2,000 an hour.
Okay, so they can shoot stuff into samples and stuff
Yeah.
like that they want, okay.
That's a good question because these are very expensive facilities. So, in US, there's a lot of money pumped from, the federal government to different funds, the Department of Energy mostly, NIH and other big fund. But in countries, for example, like Canada, if you look at the Canadian Synchrotron, it's funded by, I don't know, 2-3 provinces, the federal government, a whole bunch of universities. Like, you need a lot of money. They're quite expensive. But, to build one from scratch is probably $100 million right now, with inflation and everything taken into account. Plus to maintain, to actually operate, it's a lot of operational cost. The one in Canada actually has a liquid nitrogen magnets, superconducting, because they wanted to have a smaller one, but we get performing, so that they have a liquid nitrogen on the side. So yeah, they're pretty expensive stuff. So this is the Canadian light source. That's an old image, I think. It kind of looks a bit different now. It became operational in 2004, has 20 beam lines, and they claim around 4,000 users since 2005. It's a generation 3, so there are like now 3 generations, and the 4th one coming, including electron lasers. If you look at the Canadian light source, so what they have here in the center, they have basically an electron accelerator. They have an old linear accelerator that came from a nuclear research experiment at the University of Saskatchewan, basically site. And then they basically build on this side, and they use this linear accelerator. And then what they add is they added this basically circular accelerator. So what you do is once you accelerate the electrons, then you can move them to this storage ring. So in this storage ring, you basically just maintain the electrons moving around. And from time to time, you put these insertion devices. And those are basically magnetic fields that basically oscillate the electrons and produce the X-ray. And you see you have about 20 of them. You also need to basically maintain this electron roughly in a circle. So you have magnets who also maintain the electrons in this type of circle. So the insertion devices are 2 kinds. There are wigglers and undulators. And you can see here basically what type of magnets you need to basically maintain this electron in the circular area there. And you also need a superconductive cavity, because you lose about 1 MeV. It's actually not, it's wrong here, it's per second, not per turn, but you need to basically pump energy, so you need these electrons to be accelerated from every time they go around, because they lose energy. This is still imperfect, so after about 8 hours, you have to reinsert the electrons in movement. There are different other synchrotrons where they are able to basically do this in a continuous mode, so you don't have this shutdown time of about half an hour between reinserting electrons and accelerating electrons in basically the circle. You see here you have all kinds of magnets. You have like dipoles. You have dipoles, and you have quadrupoles and sextupoles. This maintain the electron beam to just a few microns. So the electrons basically move in that big circle. It's just a few microns. The smaller the electron beam, the more productivity you have in producing X-rays. And these are the 2 types, the wigglers and undulators. They have this kind of funny name. So wigglers basically wiggle the electrons, so they have relatively high magnetic fields, and they have a relatively large angular deviation. This is the gamma, the Lorentz relativistic factor. The electrons in the Canadian light source have about 2.90 GeV, and if you calculate this, you get about 5.7 10 to the 3. Inverting that, you get only about 1 milli, less than a milliradian. So it's a very, very small deviation that you do, with wiggles. But if you wiggle them more vigorously, you get about a continuous spectrum, and you get the brightness that depends n times with the number of magnets you have. So basically, if you have n, then you get n times the radiation for each of them. Now, undulators are a bit different. They wiggle a bit less, but you can also tune, but they have more discrete, so you can actually get more monochromatic type radiation, and their brightness depends with n squared. So they have some kind of like more constructive type interference of the radiation from each of the magnet pair. So you get a bit more radiation, and you also get a bit more brightness. And you can also tune by tuning the distance between this magnet, or you can actually tune a bit the energy. Now, the main, one of the main processes, the workhorse of synchrotron is the photoelectric effect, mostly in the X-ray region. Also, I have to mention that I'll talk a lot about X-rays, but the Gherase light source, they also work with infrared, and they even have a visible range, which is kind of strange because normally you have a lot of laser science that can do visible rays. So visible is not quite what people aim for. It's mostly in the X-ray that most of the applications are. So if you look at the photoelectric effect, you have a few actors. Now you have the incident photon, where you can tune the energy very, very fine. With synchrotrons, you can have less than 1 electron volt tuning capacity. So that's really good. And the photon being absorbed basically promotes an electron in an upper shell, or basically in the infinite continuum outside the atom. And what's left, basically, you have a K-shell vacancy, for example. You can have other vacancy in the other shells. So you have basically, from this you have the photoelectron, and then the excitation of the atom results in two other products. One is the Auger electron emission, which is an electron also with a very specific energy because it's based on this transition, the excitation transition. And then you have the characteristic X-ray or X-ray fluorescence that is used also to basically figure out what type of atom you have. And then we also have the X-ray absorption spectroscopy, which basically refers to what is the probability to have a certain photon of a certain energy being absorbed. And I'll talk about these two in particular. Now, these two electron spectroscopies, the photoelectron emission spectroscopy and Auger electron spectroscopy, I won't talk about today. However, they are used a lot, especially in the surface and when you have lighter elements. So if you actually look at the photoelectric effect, it actually dominates all the interaction up to like 1 MeV. And that's why we use, that's why photoelectric absorption is used a lot, because it basically dominates the scattering of the X-ray, the incoherent scattering, the one in the red here, the Compton cortical here, it's scattering, which is actually used in X-ray diffraction. So it's also utilized, but photoelectric, it dominates this, so that's why we use this. So nature is nice in that regard. Now, if you look at the probability of getting fluorescence or getting Auger, because these two are basically complementary, you can actually see that for heavy atomic numbers, the X-ray fluorescence dominates. You see the curve here, but for so vice versa stands for the Auger electron 1 minus omega k. You actually get better Auger electrons with lighter elements. So if you actually want to look at lighter elements, probably it's better than Auger electron spectroscopy or photoelectron spectroscopy. But if you look at heavier elements, metals and so on, it's probably okay to look at the fluorescence part. And you can actually also, the lines that are emitting, because you can have different different vacancies in different shells, and you can have different transitions, multiple transitions until the atom comes to its ground state. And they have different intensities. This is another review paper that, and the author organized this in kind of these lines, and the darker ones represent the more intense transitions, and the lighter ones are the ones that are not that intense. The K shell lines are always the most intense, and then the L shell and so on. I didn't even put here other lines. There are other lines, but they are very weak, so hard to observe. This is what an observational experimental looks like. This This is, I think, from a few years ago when we looked at the bone sample. You see you have the beam comes from this direction here, and this is an ion chamber that basically make sure that you have the number of photons that you need, and make sure that you always look at your signal depending on your initial number of photons. So it basically monitors the intensity. Then you have the detector right here. It actually has about 8 different detectors going in one, basically. And then the sample, and then you have this microscope, because we do microscopy. So you look at the sample at the microscopic level, because these beams can be down to like a few microns, and for soft tech they need a nanometer range, so you get very, very small. That's kind of like a type of experimental setup. Now, the nice things you can do a synchrotron is you can do imaging. So you can do imaging and microscopy simultaneously. So you can take a sample and basically probe in each point many, many times, and you can see its elemental composition, and you can look at spatial correlations. So that's important for biology, as you see in some of the examples. Now the disadvantage is that you have to wait a long time. And I put here just a quick calculation, just for a quarter of a millimeter square, how much time it takes. So almost 3 hours just to do, quarter of a meter. So if you imagine if you want to do the whole brain, and I'll show you some pictures of it, but not whole brain, but a big part of the brain, it would take many hours. And that's just for 4 seconds. So in 4 seconds per shooting, you need about 3 hours. So long time. And also, if you bombard a lot different types of biological samples, you can also damage them. So that's a downside of both XRFN and spatial X-ray absorption spectroscopy, where you have to spend even more time for each location. That at some point, if you do too much radiation, you can damage. So you always have to make sure, that is something like bone would be very, very easy because bone is more. But if you put soft tissues, you have to be aware of that. Now, X-ray absorption spectroscopy looks at the different things. So looks at the probability of getting of the photon being absorbed. So the experiment looks a bit different. You have to put the detector right in front of the beam, and you basically have to measure the relative absorption. So you basically measure N0, the number initial, minus the photon detected divided by N0. And what do we do is that, and you also have to do it in very, very fine steps. So the incident photon energy has to be tuned, so it's just above the absorption. In other words, you give the photon just enough energy to basically kick it over to make the absorption. And what we're looking at that is basically a quantum mechanical theory that we all call it now the Fermi's golden rule. That was actually written by Dirac in 1927, and it basically tells you that the probability of this absorption depends only on the initial quantum state and the final quantum state. So initial quantum state is the atom where the electron is basically bound and the photon coming, and then the final state is basically where electron is being basically kicked out of the photoelectron, and then you can find out this probability. So that means that it really depends on the final state, because the initial state, you assume that it's the same. But if you tune the incident photon energy, you can actually tune this final state. So this probability really depends on where the electron ends up. So you basically have what you have two regimes. If we are just above the cage. So if you look at the relative absorption, you get right over this jump. The electron gets kicked out, and you can see that there are different. If you look with the microscope of these very fine energies, you see that you can put the electron first in a 3D suction, also just in the upper shells or outer shells of the atom, and then you can basically bump it up a bit more, and you get in a 4D, and then you basically you get in outside the atom, and where it actually, what does it do? It scatters from other electrons from the neighboring atoms. So that means, what it means is that with both of these two regimes, both the Xanax, which is just around the KH, and the extended X-ray absorption phi structure, which is a bit farther in energy here, means you can actually probe the chemistry. Because wherever this electron ends up, the shape of this this structure that actually spends only, if you look here, it goes from only about 71 electron volts, and we see the fine structure only go to about 2 electron volts. So very, very narrow energy, you actually get a lot of information, you get this structure. So we can do chemistry. So with X-ray fluorescence, you get the elemental composition, and with X-ray absorption, you can actually look at the chemistry, whatever that atom that you look at bounds to. The XIF, the fine structure spectroscopy, also has an interpretation that came around in the 1970s. People looked at the electron scattering and figured out that this wiggling that was observed actually has to do with how far the atoms are from the original atom where electron got kicked off. And so this is actually from the original paper, and they took 2 samples, one is a crystalline germanium and one is amorphous. And you see the finer structure here represents basically scattering with the farthest atom in the crystalline structure. But in amorphous, you cannot really distinguish, because amorphous means that the distances are kind of blurry between the atom and the original atom. So there is a Fourier transform of that. So what also means that you can actually find out distances from the atom where electron got kicked off to the other atom. So it's a neat way to actually figure out different chemical modes. Yes?
You're showing a great example of crystalline versus amorphous. Could it also show strained classes?
Sorry?
Strained class states where you have...
Yeah, it can be using different materials for different, you can show the chemistry, but also the type of material we have. So, it's a full field just looking at these. So both AXIF and Xanax, it's called, both these regimes can actually tell you a lot about the chemistry. And I'll show you some examples in biology how it can be used. Now, in terms of advantages, is that you can also have this being very small, so you can actually probe the chemistry also microscopically. You can also use XRF, so you can use both of them to basically look at the elements and their chemistry. The challenges are, again, the long acquisitions and the radiation damage. Actually, here it's even more important, because you can actually, if you put too much energy, you can actually change, you can use chemical reactions, and you can change the chemistry. So then it's, you have to also be careful. There are some strategies you can kind of minimize that. You can, for example, cool down the sample a lot. So if you cool down, the probability of using chemical reaction is lower. Or you can put some other type of solvents or other chemicals around, so you make sure you kind of annihilate some of this chemical reaction. But that can still occur. Now, the first study I want to talk about, so moving on to some applications. In my postdoc, we looked a lot of arsenic. And arsenic tends to bind to tissues where you have a lot of keratins. So keratins are proteins, a class of family of proteins that have sulfur in it. So it binds to sulfur. And we wanted to know a bit more detail of where this arsenic can basically go, when it goes in the net, where it needs to go. So what we did is we had inside there was a fountain that had a bit higher elevated arsenic level. It wasn't too much, but it was, I think the normal, I forgot the exact numbers, but the normal range was 1 milligram per liter of arsenic. That's a normal range. Anything below that is fine, but anything above is not. So that was a bit higher than it is. And we asked for volunteers to give their nail clippings. So we had about 8 volunteers. We had their nail clippings. We put them in the resin. We basically sectioned them with a diamond cutter, and we basically had these pictures. These are basically photographs of nail cross sections. So toenail and the nails. And then we put them, we went to the Synchrotron, the Canadian light source, and we basically did this type of XRF images. And we got multiple elements. For example, you can see here the zinc. We have a lot of zinc in there. So basically the zinc is basically almost identical to it's all over the tissue. Now for arsenic, we we didn't see too much. However, wherever we saw arsenic was in the ventral and dorsal layer. So in other words, on the surface of the nail and underneath the nail. And we basically came to the conclusion that that's due to the fact that in these layers you have unstructured keratins, where arsenic can come and bond easier to the sulfur, but in the other ones you can't. So that's kind of the explanation we had for this arsenic. So you see there was some hot spot basically of arsenic where you had concentration. We also use, so these are basically these numbers here represent concentrations in microgram per grams. How we did that, we had some calibration samples made with resin, and we compared that signal with that, taking into account everything like sickness and so on. So you see that we had up to like 9 or 8 micrograms per gram. That's actually quite high for and then the group from Canadian light source who does X-ray absorption spectroscopy, the group of Grant, George, and Ingrid Pickering, so okay, maybe we can take one of these hotspots and do X-ray absorption spectroscopy. So we collaborated with them. They took our samples and they ran X-ray absorption spectroscopy on them, and they got this kind of spectra. So these are the X-ray absorption spectroscopy of arsenic, and you see they have different shapes. These are the exotic, so these are just above the binding energy. You see the binding energy for arsenic is around 7.87. And you see these, you see 2 peaks here for certain types of arsenic compounds, and you see 1 peak, and so on. You see different areas. So what you have to do when you see an experimental peak, you try to fit with standards. And also this group, they are quite well known in X-ray absorption spectroscopy, and they have different standards, their own standards. And they're able to fit the experimental spectra from the nail with all these type of standards. And from the fitting, they were able to obtain how much concentration would be arsenic in a certain compound was opposed to being in another type of compound. In other words, the species, what is called the chemical species. And they figure out by doing this analysis of the spectra that most of the arsenic is an arsenic 3. So this type of compounds, see this arsenic and this kind of oxide. This is a glutathione. It's basically a very common protein in nails and other tissues. And then they saw some arsenic 5, but not too much. You see the percentages are only one sample, they saw a lot more. The rest is mostly arsenic 3 in different forms. Now, we also did about 7 years ago a different study. We're trying to figure out, we're trying to look at lead bond. That's actually David's area of expertise. He's done that for 20 years since this area. And we're trying to figure out what is the best X-ray tube that you could use to measure lead. Now, the idea with lead is that it has a very high binding energy, about 88 keV. You could actually do a big X-ray tube that excites the energies above that. But this would be kind of unpractical, and if you want to, hold this around, go to communities to measure lead bond, it would really not be good. So I said, what if you actually excite the L energy? Well, the L energies are actually much lower. So you get like, all above below 20 keV. You can actually have small X-ray tubes doing that. But we said, what would be the best target of the X-ray tube? Because if you put a certain target, the X-ray fluorescence of that tube can actually be used to excite. So we look at 3 different elements. We said, this X-ray tube is made of zirconium. It gives off these energies, which can excite most of the energy except for maybe for this one. It's a bit below 50. And then niobium, it's basically really good. It excites all the shell energies of lead. And then molybdenum, actually molybdenum is used in mammography, because in the breast cancer, the best contrast for breast cancer is around 20 keV. So this molybdenum is being used for many years now. Mammography X-ray tubes are different from all the other X-ray images because of that, because they are the best energy to basically detect and monitor for breast cancer. So we look at all these 3. So at Synchrotron, we didn't actually have to make any of the tube. We just basically tune the energies for these 3 materials. And we also picked two different geometries. We picked a 90-degree basically geometry. We put the bone, we had like a very simple bone, this is kind of like a square bone, and on top of it we put the resin to basically mimic the soft tissue. And then we also look at the basically a more backscatter geometry. So the angle here was 175 degrees. And wanted to see which one of these geometries and which of these three energies is the best. And we also put a bare bone where we remove the soft tissue. And when we look at the data, so the data look like that. You know, so if you, this was all for 90-degree geometry, the bare bone looks like that, and the soft tissue looks quite different. You see here the scatter peaks, the conton and the coherent are much larger. So that soft tissue really impedes. You see how, and also the attenuation of the soft tissue. These are the lead peaks with the bare bone, and look how much smaller they are for the soft tissue. So that's what we have. Some other elements you always have to look out for different contaminants in your sample. Some of them come from the metallic parts around. This is obviously the calcium. When you put the soft tissue, you almost don't see the calcium, despite the fact it's very high concentration of bone. It's about 20%, and even in this bone band, it's just very large. And when we look at the, so we did that, we did these 5 different concentrations of lead, and look at the calibration lines, and we look at the slope of the calibration, and in other words, the sensitivity of the approach. And you see for bare bone, you get these curves. The black one, which corresponds to 90 degrees, is always lower than the red one, which corresponds to the 135 degrees. That's because of the collimation cross section. It's always the backscatter is always lower than that, so you actually get the better signal with the larger angle, the scattering angle. Now, the problem is when you put the soft tissue between, and then we also notice higher, obviously, sensitivity at the 16.0 or 15, which were corresponding to the zirconium. So closer you are to the binding energy, the better you are for bare bone. For most cases, for most lead energies, you're better at least closer, which is what is expected. However, when you put the soft tissue, you no longer see pretty much any difference. All the three energies pretty much seem the same, except again that the backscatter geometry gave you a better signal because of the background, because of the scatter, multi-scatter. So that was the conclusion that no matter what energies you pick, when you put the soft tissue, they're pretty much all the same. So it was a good use of the synchrotron trying to get to a practical problem. Another example, there are many examples looking at cancer. This particular one came from an Australian group, and they looked at selenium. It appears that selenium has an anti-cancerogenic effect. It actually kills cancer cells. And the group wanted to know what is the chemistry behind it, what are the mechanisms. So they basically look at the lung cancer, which is, again, one of the cancers, more aggressive than people look at it. And they took this cell, and they had 3 different experiments. One was a control experiment here on the left, where they simply put a phosphate buffer saline, basically was like a control type experiment. And then they put sodium selenite for about 20 minutes, and they get these images here, which are lower. And then they put a longer 24-hour exposure of that cell to this the selenite solution. And what they notice is that if you actually look here, you see after a while, you kind of see the cell kind of takes on this buffer saline solution. And at this point, you see this is just a simple image, microscopic optical image. You kind of no longer see the membrane, so the cell is basically dying. But they wanted to see more, to see what really happens. And if you actually see, you see the zinc, for example, gives you clearly the boundary of the cell. But here, the zinc is no longer white, and then here, in this longer exposure, basically, you can see the zinc is basically moving away. So in other words, the cell is basically dying. The membrane is no longer working. But what was more interesting is that they look at the copper and the selenium compound, and they actually notice that here you have some selenium. Here you have very low selenium because there's actually nothing in the solution. So it's basically background. But then they notice that it's increasing here, and then here it actually all accumulates towards the nucleus of the cell. And the same with copper. You see initially it's basically like very fuzzy, almost nowhere, no concentration, the same here. But then it kind of starts to concentrate in this basically dying source. So they figure out that it must be something about selenium and copper that led to this cell death. Okay. This is a scattering image here. So basically scattering, you kind of see like a very fuzzy image of the cell. You see here, and here you kind of no longer see it. It's kind of everywhere, basically dissipating. And then they also took, they did an X-ray absorption of the, to figure out what happens to selenium, what does it bind, where is the mechanism. And when they did that, again, they took different standards of selenium, different, basically something, all the compounds that would be suspicious or would be expected. And they noticed that most of the selenium came either in an elemental form, and that would be somewhere around here, or in this selenoplutonium. This plutonium is basically a type of alcohol where you replace the OH with sulfur, so it's basically a sulfur compound. So it seems like selenium and sulfur, they sometimes bound. However, when they look at the XIF, the fine structure spectrum, and they did the analysis of the Fourier transform, they noticed that these binding legs corresponds to a selenium-selenium bond, but not a selenium-copper. So selenium and copper didn't bind together. They didn't have any compound. They were basically separate. So they basically came to the conclusion that the cell death must have something to do with the copper, but they didn't see the selenium copper. So it's basically the processes were independent. The reason the cell died was because of copper accumulation, but selenium and copper were not involved. But this is the type of research where you use both X-ray fluorescence to localize, but you also use the X-ray absorption to figure out what is going on in the biochemistry. And you cannot really do that with anything else because it's hard to, in a microscopic scale, to figure out. You cannot do, traditional chemical methods where you take a piece. This one you can do it in vitro, or you can do it on the spot. Another also cancer, but this time bone cancer, was done by a group, the Austrian group, which is actually very, very active in the bone type medicine. They actually had invented an electron microscopy looking at the bone method in the early mid-90s. And here what they did is they took osteosarcoma bones, so you see here basically the cancerous part of it, and they zoom in on an image where you can actually see some cancer bone, but you also see some healthy bone. And you can actually see here, basically that's the healthy part and the cancer part. And they basically had two regions of interest, this region and this region, and they looked in a bit more details in these two. And they found basically that both zinc, so what you see this is the calcium distribution and zinc, both the calcium and zinc were much higher in the tumors than in the healthy region. You see actually black here for zinc, and then calcium here again. And they also saw this type of features. That's the type of research that's done a lot with respect to cancer and other diseases to figure out where metals basically distribute. And the many diseases, cancer including neurodegenerative diseases, as you see in a minute, they observe this a lot. They don't know exactly why that's happening, but it seems like metal metabolism, or the abnormal metabolism, puts elements in a different distribution than a normal healthy tissue. Another interesting research came from an Italian group who look at asbestos. I mean, we know now for many years that asbestos is dangerous and it's actually carcinogenic. but people didn't know how it's cancerogenic, how it does it act on the lung. So they first did like a normal biological type assessment. This H&E type staining figures out where is the nucleus of the cell and where is the rest of the cell. So it's a type of cell, and you can see here with the arrows that you can see areas where they're so-called diffuse fibrosis. So you basically have a bunch of cells coming together and basically forming this fibrosis, this type of longer type, organism in the lung. And then the asbestos bodies. So what are these asbestos bodies? That where this micrometer or lower or even smaller pieces of asbestos come and they're basically macrophaged by the actual cell. So it's a defense mechanism of the lung. It tries to basically macrophage this and basically defend the body against these very small pieces of asbestos. And then they actually did a more specific type of histological microscopy. So this is all classical microscopy. They did a ferric detection. It's called Kerr staining, where they actually saw in the black, you see again, you see the pieces of asbestos macrophage, and you can see long pieces. But you also see in the blue arrows, it's hard to see here, but there is some pieces where they're not macrophage, so they don't appear as black in the staining because the iron has not changed. So this part here have a different iron metabolism, and that's called basically non-hem or ferric iron detection. In other words, it's a type of iron that's not found in the hemoglobin, it's not hem, it's not part of a bigger protein, but it's more loose, more in an inorganic form. And that's what they looked at. They wanted to look why is this iron metabolism? What has to do why the asbestos? How does it come that it forms this? And they look at different elements, not just iron. So if you see here, it's basically they look at this piece of asbestos. So these are very, very small scale. You see what the magnitude of. Yeah, this is basically an 80 by 20 micron. So 80 and 20 microns. And you see how basically for iron, you see iron metabolism, it's much higher than any normal tissue. It's a huge accumulation of iron. And it's not just the iron in the actual asbestos itself, but it's iron coming from the other cells. And calcium and sulfur also seem to be like, somewhat accumulating. This is the silicon. Silicon is actually in the asbestos because asbestos is a silicon and has iron too, but it's a silicon compound. So it's used for insulation. But that's why it breaks down in very, very small pieces. So silicon is part of it, but you see that there's a lot of accumulation of other metals, and even magnesium is involved here. That's also assuming magnesium. And they also did this XRF mapping. They also did soft X-ray imaging, where they actually zoom in on a piece like this magnesium. And what they also did an X-ray absorption spectroscopy, and what they noticed is that most of the iron in this phagocytated asbestos pieces was basically in this it was this in ferritin form. So they basically said that this transformation of ferritin to ferrohydride and hematite is basically universal to this abnormal iron accumulation, and that's basically what they notice here. They basically assume that this iron abnormal transformation, so chemical transformation, also accumulation, has to have something to do with the carcinogenic effect of these asbestos fibers. I had the brain study. Yeah, I skipped over. Sorry about that. I skipped over this brain study, also from the group of University of Saskatchewan. They look at Parkinson and normal human brain, and they did some really nice maps. They actually did a lot of work trying to minimize the time that you basically can acquire these images. And so they did less than 2 seconds per pixel they took these vertical steps of 40 micron, and they looked at the area of the brain that's affected by the Parkinson, and that's this basal ganglion is somewhere in the middle of the brain and is responsible with motion control. As you know, Parkinson has a lot to do with it. You look at the normal brain images here, and you can, the abnormal Parkinson brain is down here. And you can see for both spirals, so the red one is iron, and the blue one is zinc, and then the other one is a combination. When you see how much less concentration you have for zinc and iron, and in different areas, you basically have these are much brighter here, and this one is really severe. So this one is an opposite effect to what we saw in cancer, where we had a lot of accumulation. Here we actually see less, and this was known too, but wasn't known into that detail, anatomical detail. And these are basically the first group who did that. There are some MRI studies where you can actually also look at iron, but these are much more detailed, and they were able to do that quite detailed. As you see in the piece of the brain, very large piece. So these are millimeter. The scale area is 5 millimeters, so these are several millimeters, almost the entire part of the organ here that we're able to reach. I think that's the last few examples. So in conclusion, I didn't mention many of the other techniques that you see in synchrotron. What I wanted to say is that there is a synergetic effect, there's a synergy between XRF and XIS, but also other methods that I didn't talk about, especially in biology, the micro X-ray computed tomography, where you can do CT, micro CT of small cells and tissues. This new method called X-ray pictography, which is basically an X-ray diffraction type imaging. So in the same time where you're taking X-ray fluorescence and X-ray absorption spectra, if you put a detector that looks at all the photons scattered in the forward direction, you can actually reconstruct the object. So it's a computationally intense image where you take all the images, whereas you scan across the map, and you can actually find out the object. And and it can be done also in 2D and 3D. And of course, the classical X-ray diffraction, where you can look at molecular structure, and that's done a lot in synchrotrons. And of course, it has a lot of applications, especially in drug design, because they want to design certain molecule by molecules that can help, bind to other molecules in the body. Plus, also decipher all the proteins we have. As you see, there's a lot of active research in that area. I haven't done any research in X-ray diffraction, but it's used in synchrotron because you can have these very intense beams, very directional, so that's perfect for very good diffraction. I'll stop here and I'll take any questions.
Questions? Yeah. So, selenium and zinc destroy cancer cells?
Zinc has a lot of role in basically the immune system. In selenium, it appears to have some, anti-carcinogenic role, but yeah, it's not really known why. Selenium is actually, it's an essential element, so your body needs some level of selenium. But it seems like if you give a bit more targeted to a certain area, it might help. So that was kind of like an attempt to look at the biochemistry, what selenium compounds actually do in terms of how they act.
Understanding the So in the X-ray fluorescence and the X-ray absorption spectroscopy, when you were looking at
the lung cell with cancer. So there was a high concentration, the bone cancer. I forgot which one, where it had a high concentration of zinc. Was that already known before, that concentrations of zinc in bone cancer?
Yeah, it's been known, I think this I know. This has been known that in cancer, all the elements, I talked to Jason Bush, who's an expert in cancer, yeah, it's well known. And this one is basically just an experimental confirmation that indeed in cancers, in almost all types of cancer, you have this unknown distribution. In this case, you actually have more zinc. So people, they don't know why. It's probably an immune response. The metabolism just gets out of whack. This is actually a fairly simple study. They just basically did these images and said, oh yeah, look at that. That's what happens.
Okay.
In terms of the mechanism, why is that occurring? Why you have sometimes accumulation, sometimes you have lower than normal. People don't really know, and they try to figure out because you have different actors involved. You have to also look at the chemistry, so that's what the X-ray absorption part is. This study didn't do any X-ray absorption part, but yeah, there are many things involved. It's quite complicated, but it seems like those calciums. This was actually about 6 times higher in tumors than even normal tissue. It's some kind of quantitative approach. Yes.
So is there a lot of work done where they got a huge database and they're getting a lot of information, a lot of sampling from different places? And
I think different groups, they go to Synchrotron and they publish their own data. People at the Synchrotron, the beamline scientists, can actually do their own research. And in fact, for us, most of our studies were done with beamline scientists. You can propose a project, but you have to prove very strongly that first of all, that nobody else has done what you're trying to do, and also that you need to use Synchrotron, because for many studies you can use normal lab type devices. So yeah, the applications can be quite competitive. You have to really prove that you need, and you have to apply to the right beamline, because they have beamlines that are specialized in X-ray diffraction, beamlines that are specialized in X-ray fluorescence or X-ray absorption or other type of microscopic techniques.
that was my next question. Could you say, I want to use this beam line and this beam line and all that?
You have to justify why. You have to put everything in the plan. How much time, what you're planning to do. When you go there, they help you. If you don't help you, you wouldn't be able to do anything, because you see 10 screens. It's like, I don't know how many devices, and if you don't work there, unless you work many, many times, you don't know how to use it, or a bit, but the beamline scientist is helping. And actually all the users, the industrial users, also do that. So the time of the Synchrotron is usually divided in 3 parts. One part is scientific, where anybody can apply for a project. One part is industrial, where people have to pay for a particular, they want to look at the sample or something. And then 1/3 is for development, where they actually, expand on beamlines, or they go on calibration, make sure everything is. And that's their own time. That's the beamline scientist. And those guys are hired full time. Yes.
What are some of the industrial applications that was sent for this really?
Yeah, that's a good question.
They
I
dope
know
all
that
kinds of
when
stuff.
we went to the
Yeah.
summer school, there was a
Hard stuff to
photoelectron or energy electron spectroscopy person who gave us a talk about that, and he said that one time a yogurt company in Austria, came telling them that basically the cover of the yogurt, the aluminum part didn't stick, and they didn't really know why it didn't stick, and they lost a lot of yogurt. So with this photoelectron, which is basically a surface type science, they were able to determine what was wrong with that particular stuff. But they have different ones. I mean, the biochemical companies, it's always a diffraction. People want to find out, the structure. For X-ray fluorescence, you can, I heard that people, put different, they can find composition of different metals. I mean, there are some applications where you don't need to use a signal. but there are some particular ones that you do need to use a synchrotron. If you want to do that, especially look at the microscopic part of it, you cannot use X-ray. But it's starting to be, better for the lab-based experiments. Like the beam I have is 20 micron, which is very large compared to this or below that microns. But you can still do decent type of XRF. But yeah, you have to really prove your case. I don't know exactly what type of industrial applications they have, but that's a way. It's a source of revenue. It's a source of money because they're very expensive. I think Canada wanted to have one for like 70 years. I think it's since the early 50s and only the early 2000 finally.
Actually, Mihai, so we went on a tour
To the light source, yeah, exactly.
The Lawrence Berkeley one. And I don't know if it was Synchrotron, but basically they had a whole, Intel had a whole thing where they were using something to scan their chips down to very like micron.
Right. They were paying for a whole lot of the actual
Electronic
operation.
industry
Yeah.
uses.
I don't remember whether it was Synchrotron or whether it was just like very short optical wavelength light. That I don't know.
No, it's probably. I have some pictures where the people took XRF images of the chips and you can actually see detail and everything. But yeah, the electronic chips, especially for, I know this from other type of research, that they have these multiple layers of electronic for, especially for cell phones. They pack a lot of electronics in these cell phones, and apparently to have these very copper layers, they have to be like very pure and very, they have to be known very well. I guess the structure, I don't know exactly. So that's the type of applications where we have to look at both the chemistry and the structure, fine structure. And then for silicon, actually XRF, because silicon for electronic has to be very pure. It's one of the purest. It's like 99.999%. It's very, very, has to be very, very pure form, because then you have to dope it very precisely. And the smallest the circuit, the purity has to come home. So that's the applications.
So any other questions, comments?
I wanted to say that you cited Ivanenko.
Oh.
Ivanenko was my and Merab Gherase supervisor for at Moscow State University. He was not a good guy, he was a good guy. But, okay, he had the right, being the guy who supervised scientists. He put his name, Fok Ivanenko, Spinoz. He put his name, nuclear model of nuclei with Gapon disappeared. Now I see with Pomeranchuk, really Pomeranchuk. And when I was in Tomsk, I was a graduate student in experimental nuclear physics. They created Betatron. Was it called?
Yeah, I think that's what their paper came. I think they were also interested in astrophysics from what I understood. So that paper came, and these guys, the Americans, realized, oh yeah, these guys are looking at that. That's interesting, and that's other people.
So I will send you. There is a book by Joe Sneak, How to Do Science Under the Stalin. My name is also on the front page. Because my collaboration with Vaneka, he's supervising, I was arrested and put in prison in a special gang for dissidents at Moscow University. Merab survived, he had a protection from Sardanashvili, so this world is very small.
Wow. That's a story.
Your supervisor, huh? So he was your supervisor?
Yeah, from formal point of view, it was my PhD supervisor at Moscow University.
So any other comments, questions? Okay, well, if not, let's thank you.